Let's solve some kinetics problems here. And there are several kinds that we can do. On this video, we'll start with the reaction rate and order diagrams. First of all, you cannot write a rate expression from a balanced equation. And also, the rate expression is not the rate law. It tells us what we're looking for in a rate law experiment. So, for example, this reaction of hydrogen gas with iodine vapor to form hydrogen iodide. The rate expression could be the rate of disappearance of the hydrogen, which, as you can see, is disappearance here. The rate of disappearance is a function of time. That's 1/2 the rate of appearance of the hydrogen iodide. So we could write the rate either way. This tells you what you want to measure in the lab. Now, your turn. The equation is copper reacts with silver ions to form copper ions and silver. And of course, only the silver and copper ions would have a concentration. We have here two expressions by which we can measure the rate. The rate of disappearance of the copper wire, or metal, is 1/2 the rate of disappearance of the silver. See the stoichiometry in the equation. And the rate of disappearance of the copper is equal to the rate of appearance of the copper ions, the blue, in the reaction. And it's also equal to 1/2 the rate of appearance of the silver metal. Now, how to find reaction order from concentration versus time data. What we need is a chart of the concentration of a reactant that we are studying as a function of time. The product would be a fast graph of the natural log of the concentration of the reactant versus time, or the reciprocal of the concentration of the reactant versus time. That's what we need to see in order to determine what reaction order we're working with. If the graph of the natural log of the concentration of the reactant versus time is a linear graph, it's a first order reaction in reactant A. If it's a curve, it's probably a second order reaction in A. If the if the concentration of A versus time goes down in a linear fashion, it's one of the rare zero order reactions, which means that the rate is not dependent on the concentration of that particular reactant. So, reactant A changes concentration with time, as you see here. What is the order of the reaction in A? Why don't you plug these numbers into your graphing calculator, find the natural log of each, and then produce a graph of the natural log versus time. If you do that, the natural log versus time, we get this. This is not a straight line, therefore it is not a first order reaction. It suggests it's probably a second order reaction. Now let's suppose we look at the butadiene concentration with time. Here's the data in this reaction, and we want to know what the order is. So find the natural log of each of these concentrations of butadiene. That's a period, by the way. And plot it against the various times here in seconds on your graphing calculator. When you look at the natural log versus time, we see this curve. We've plotted a straight line here between these 2 points to show that it is not a straight line with all these points. This reaction then is very likely a second order reaction, certainly not first. There's another way of finding the reaction order using the initial rates of the reaction. This is a favorite of test writers. You're given the concentrations of all the reactants and the rate of reaction for each set of conditions. You then have to identify what is being controlled between two runs and what is changing between those two runs, and determine how the rate is affected by changing that concentration. What you want to do is look for a doubling of the rate when the concentration of one reactant doubles, or a quadrupling of the rate when the concentration of that reactant doubles. Everything else needs to be held constant in order to make this work. So, given the following data, determine the order of reaction in sulfur dioxide and in oxygen. Look for doubling of concentrations with the other concentration being held constant. So here, for instance, the SO2 is being held constant, and between number 1 and number 3, the oxygen is being held constant. If you look at the 2 to 1, the oxygen concentration is doubling while the sulfur dioxide is held constant. And the rate of formation of the trioxide is going from 0.6 to 1.2. That is also a doubling of the rate going here from this smaller number to this larger number. So this is going up at the same rate. It's linear. So the rate is directly proportional to the concentration of the oxygen gas. The reaction is first order in oxygen gas. When we look at 1 and 3, we see that the oxygen concentration is the same. The sulfur dioxide concentration is going from 0.3 to 0.6, which is a doubling. And that means if you look at the rate, you see, the rate is quadrupling, going from 1.2 to 4.8 times 10 to the negative 2. So this is 2 squared, or 4 times the initial rate here, and this is doubling. So as this doubles, this is quadrupling. That means that the rate is proportional to K times the sulfur dioxide concentration squared. The reaction is second order in SO2 because the exponent is a 2. Now, since the reaction is first order in oxygen and second order in SO2, we can now write the overall rate law for the entire reaction. It is K times the sulfur dioxide concentration squared times the oxygen concentration. We can then solve for K. That's the rate divided by the square of SO2 concentration times oxygen. If we use our experiment number 1 from the prior table, we plug in the rate, we plug in the concentrations, and we do the multiplication on the bottom and the division between the two, and we get a rate constant of 0.667 for this. Why don't you try it with another set of the numbers from the previous slide. Now that we have reaction order, let's see if we can fill the table in here. If K is 0.667, the reaction is first order in oxygen and second order in SO2. So in experiment 4, if we divide the rate by 0.667 and by 0.2 squared, we would get 0.37 molar as the initial oxygen concentration. Now let's predict the rate of forming the sulfur trioxide in experiment 5. Again, we have the rate law down here at the bottom. You just plug in the numbers and solve. And you should be able to do number 6 by yourself now. So here's the answer to number 5. And that's an exponent minus 2 here. And you can do number 6. Now, how do we find K from the concentration of the reactant and the rate data? So let's look at a first order reaction we've already examined. The rate here is minus 0.240 times the concentration of A from the equation of the line that we see up here. And K is the negative of the slope, or 0.240 here. Suppose we have the data but no equation and know it's first order. If we look at experiment 1 and 2, we can assure ourselves that this is first order in A. See how it doubles here? And the rate, initial rate, also doubles. Now if we look at experiment 1 and 3, keeping this constant, the A constant, we see that it's second order in B because this is doubling and this is going up 4 times while C is being held constant. Looking at experiment 3 and 4, we see that this is a second order reaction in C because this is doubling, this is tripling, and this is going up by 9 times. So the rate law is, the rate is K times the concentration of A, B squared, and C squared. So we solve for K and we plug in the numbers from any of the fully known data lines. We can use any one of these to find it. The rate, K, is the rate divided by A, B squared, C squared. So K is 2.85 times 10 to the 12th. And this is harder than anything you'd ever see on a test. Your turn. Find the value of the rate constant for this reaction given this data. This is the original concentration of the nitrogen monoxide, the original concentration of the chlorine, and this is the initial rate. Remember, the first thing you do is find the order of the reaction in both reactants and write the rate law, then plug in to solve for K. Here we go. The rate law is K times NO squared times Cl2 concentration. So K is the rate divided by those two things. And if we plug in any of these numbers, it's 1.8 times 10 squared, and you can see the rather complex units that accompany it. Now, how to calculate the half-life from K? We'll stick with first order reactions here. Remember that the half-life is 0.693 divided by the rate constant. Suppose the rate constant for a first order reaction is 1.8 times 10 to the negative 4th reciprocal seconds. What's the half-life? And if the initial concentration is 2 molar, what will it be after the reaction runs for 7,700 seconds? Well, we do the math here and we see that the half-life is 3,850 seconds. Now, 7,700, which is our given number of seconds over 3,850 is 2, so there's 2 half-lives. In the first half-life, the concentration goes from 2 to 1 molar. So in the second half-life, it goes to 0.5 molar. This is a fast way to do half-life questions, where you don't actually have to plug anything into the equation with the various concentrations. Here's your turn. What are the rate constant and half-life given that is 45% complete in 65 seconds? Here's the arithmetic and the half-life. We'll complete this and then go on to another one at a later time.